This video is going to give you an example of how to solve for the eigenvalues and eigenvectors of a particular matrix. So our basic learning objectives, we need to be sure first that given a matrix we can find the characteristic equation, which is a polynomial equation that allows us to find our eigenvalues. Once we have that equation, we need to know how to factor that polynomial so that we can find our eigenvalues. Once we have all of our eigenvalues, for each eigenvalue we will find the eigenvectors by finding the null space of the original matrix minus lambda I. Or some textbooks, including ours, say that we should really think about lambda I minus A. They have the same null space, so it doesn't really matter. Finally, I want to illustrate how to check if a vector is a valid eigenvector. So here's our matrix. We want to find the eigenvectors and eigenvalues of this 3 by 3 matrix. So we're going to need to start by finding the eigenvalues. Once we have our eigenvalues, we'll find our eigenvectors for each of those. Alright, so first we need to find the characteristic equation. The characteristic equation is found by taking the determinant of A minus lambda times the identity. So what that means is we're going to take our matrix, our A matrix, and we're going to subtract the identity matrix with lambda on each of the diagonal terms. So 2, 1, 3, 1, 2, 3, 3, 3, 20, and we're going to subtract lambda 0, 0, 0 lambda 0, 0, 0 lambda, and find that new matrix. So that will be the determinant. You can actually go straight to this if you want. We're going to go the determinant 2 minus lambda 1, 3, and then 1, 2 minus lambda 3, and 3, 3, 20 minus lambda. We're calculating that determinant. And notice that I used straight bars, not brackets, because I'm calculating a determinant. So how do I calculate a determinant? Well, I expand along a row or column. And I don't really have anything clear that suggests anything is better than anything else, so I'm going to expand along that first row. So we start with the first term, 2 minus lambda, and then we multiply by the cofactor of that 1, 1 term. So we are going to temporarily eliminate the first row and column and use this minor for the determinant. So we get 2 minus lambda, 3, 3, and 20 minus lambda. And then we have our second term. We're going to add to that 1, but our determinant, our cofactor is now a negative sign, so we'll change the sign and take the determinant of 1, 3, 3, 20 minus lambda. And then we'll have our third term. Again, this cofactor is going to keep the same sign, so we don't have to change anything. And I have 1, 2 minus lambda, 3, and 3. Now that I have this, I'm going to calculate my determinants of each of the 2 by 2 terms using the simple 2 by 2 product formula. So we get, let's see, 2 minus lambda times 2 minus lambda times 20 minus lambda. And let me just finish all the work and I'll be right back. Alright, so I found the rest of the determinants. Here's the first 2 by 2 determinant, the second 2 by 2 determinant, and the third 2 by 2 determinant. Now what I need to do is I need to expand all these terms and multiply it out. So for example, let's just get started here. I'm going to have 2 minus lambda, and then I have 2 times 20 gives me 40, and then 2 times minus lambda, that's negative 2, negative 22 lambda, and finally plus lambda squared minus 9. And now let me finish up the rest. And now that I have that expanded, I need to distribute this 2 minus lambda across this multiplication, and I'll also simplify these terms. So again, you don't need to watch all that, so pause it, work through it, check your answers. So here I have the first term that's been distributed, and then the second term, and then I've expanded the other terms. So let's now group things. So we've got lambda cubed, there's only one term, so I get that's equal to negative lambda cubed. Let's identify all of our lambda squared terms. There are 2 of them, so I get 24 plus 24 lambda squared. Now let's identify our lambda terms. Let's see, we've got minus 44 minus 40, so that's minus 84, plus 9, so that's minus 75, 74, minus 65. So we have minus 65 lambda. And finally we have our constant terms. Let's see how many of those we have. Let's see, we've got 80 minus 18, so that leaves me 62. Puts me at 42. And those all cancel each other, so 42. So plus 42. So that's my characteristic polynomial, and I need to solve the equation negative lambda cubed plus 24 lambda squared minus 65 lambda plus 42 equals 0. Alright, now that we have a cubic polynomial, we need to find all the solutions to that polynomial equals 0. This requires that you remember a little bit from algebra, and in particular, we're actually going to use factoring. So if I look at, there's something called the integer root theorem, and the integer root theorem says we look at the constant term of our polynomial, and if the polynomial has integer coefficients, we look at that last constant term, and we find all of its factors. And so that's plus and minus 1, plus and minus 2, 3, let's see, 42 is 6 times 7, so 2, 3, not 4, 5, plus or minus 6, plus or minus 7, plus or minus 21, oh, let's see, 3, didn't get the 3 in there, 14 I guess, plus or minus 21, and plus or minus 42. Those are the only possible integer roots. And one way that I could do this, if I have a graphing calculator, and you're not going to have a calculator on a test, but for practice problems you can actually look at a graph. So I plug this polynomial into my calculator. Here's the polynomial. I had to change all my lambdas into x's, and I graph it, and I see that my graph crosses the axis at what appears to be lambda equals 1 and lambda equals 2. So we've got lambda equals 1 and lambda equals 2. And I need to use factorization to be able to see if that's really true. Now, if lambda equals 1 is in fact a root, lambda minus 1 is going to be a factor. And if lambda equals 2 is a root, then lambda minus 2 will be a factor. So I need to see if I can factor that polynomial. One way to do that is long division, and the faster way is actually to use synthetic division. So we're going to see about the lambda equals 1 by doing synthetic division. So we're going to test the root of 1 with our coefficients -1, 24, -65, and 42. Alright, so always start with 0. We're going to add and multiply. 23, 23, -42, -42, and 0. And since this is 0, we know that it is in fact a factor. It's lambda minus 1 times negative lambda squared plus 23 lambda minus 42. And that's equals 0. Now I knew that lambda equals 2 was also a root, so we can write lambda minus 1. And I guess we should check our polynomial, -1, 23, -42. We're testing lambda equals 2. So -1, -2, 21, 42, and 0. Sure enough. So we get lambda minus 2, and we read off the last polynomial, negative lambda plus 21. So the factorization, by peeling off these two roots, lambda equals 1 and lambda equals 2, factoring them out, we find in fact our third root. So we have lambda equals 1, lambda equals 2, and lambda equals 21. These are my eigenvalues. Next, we'll need to find out what the eigenvectors associated with each of those eigenvalues are. So let's start with the eigenvalue lambda equals 1. What we need to do is we need to find the null space of A minus lambda I. So with lambda equal 1, we need to find the null space of the matrix A minus lambda I. So here we're going to subtract the identity and see what that new matrix is. So I get 1, 1, 3, 1, 1, 3, 3, 3, 19. Now the null space is asking, so this is a matrix, and the null space is saying what vector can I multiply by and get back the 0 vector, and this is a system of equations. So when I want to solve my problem, I'm going to take this matrix and I'm going to find the reduced row echelon form of the A minus lambda I matrix. So recall that was 1, 1, 3, 1, 1, 3, 3, 3, 19. And we'll do row operations. So I can start by taking row 2 and replacing it by row 2 minus row 1. And I can do row 3 and turn it into row 3 minus 3 row 1. So here's the first step. Now what we're going to do is we're going to swap row 2 and row 3. So row 2 and row 3 will switch places, and then in the next step I'm going to replace row 2, the new row 2, by 1/10 row 2, so that I can get a 1 in that spot. Now finally, with a 1 in this spot, I can eliminate the 3 by taking row 1 and replacing it by row 1 minus 3 row 2. And this is going to give me my final reduced row echelon form matrix. My reduced row echelon form matrix gives me a new system of equations that's in a reduced form. So if I think of this as x, y, and z, that I want to multiply and have this equal to 0, 0, 0, that would be the system of equations. I get a system x plus y plus 0z equals 0, z equals 0, and I have an equation that starts with x, I have an equation starting with z, but I have no equation starting with y, so y is my free variable. So y is free. And we can give it a parameter, say t, because it's free, and solve for x. X is going to be equal to negative y, so that's negative t, and this allows me to solve my system. My vector x, y, z has to be of the form negative t, t, 0. And so I can choose any t I want and scale it. I like to factor it out. Negative 1, 1, 0. And any multiple of this vector is my eigenvector. That's what the t stands for. It tells me I can multiply by anything I want. So some possible vectors might be negative 1, 1, 0 or 2, negative 2, 0, as long as my first and second coordinates are opposite one another. And I found my eigenvectors. So let's indicate this. So I have an eigenvector, negative 1, 1, 0 is an eigenvector with eigenvalue lambda equals 1. And now let's go to the next one. Alright, we do the same thing. We start with our matrix, we subtract lambda I, so here lambda is 2. So we're going to take our original matrix, 2, 1, 3, 1, 2, 3, 3, 3, and 20. And we're going to subtract twice the identity. And we get 0, 1, 3, 1, 0, 3, 3, 3, 18. And I need to find the reduced row echelon form of this matrix, because I'm solving the system A minus lambda I times a vector equals a 0 vector. So I want to find the reduced row echelon form equivalent of that system of equations. So what do we need to do? We're going to start with our original matrix and swap row 1 and row 2. So I get 1, 0, 3, 0, 1, 3, 3, 3, 18. And now we're going to take row 3 and replace it by row 3 minus 3, row 1, to give me 1, 0, 3, 0, 1, 3, 0, 3, 9. Now I'm going to replace row 3 by subtracting 3, row 2, and that actually eliminates that second row. So 1, 0, 3, 0, 1, 3, 0, 0, 0. And I'm done. This is my reduced row echelon form. And I'm going to interpret it. If I think of this as 3 variables times that matrix equals 0, 0, 0, then I get 3 equations. I get x plus 3z equals 0, y plus 3z equals 0, and the third equation, 0x, 0y, 0z equals 0. We don't need to write that down. So, x and y are not free, but z is free. So we can say, alright, my z is free. We'll give it a parameter that allows me to solve for y and for x. And my solution vector, x, y, z, has to be of the form negative 3t, negative 3t, and t, that I can factor out the t, negative 3, negative 3, 1, and that tells me what my eigenvector is. So x, any multiple of negative 3, negative 3, 1, is an eigenvector with eigenvalue lambda equals 2. Now we find the eigenvectors for eigenvalue lambda equals 21. We do basically the same thing. A minus 21 identity. So we're going to, I'm just going to subtract that 21 off the diagonal terms. So I get negative 19, 1, 3, 1, negative 19, 3, and then 0, 3, 3, negative 1. Let's see, well, how will I approach this? I'm going to move row 1 and row 2. Then I'm going to take row 2 and add 19 row 1s. And I'm going to take row 3 and subtract 3 row 1s. And now I want to just notice that these rows are multiples of each other. I need to get something that cancels. And in fact, it's easiest here to say I'm going to replace row 2 by row 2 plus 6 row 3. And then after that, I'm going to replace row 3 by row 3 divided by 60 to get rid of that leading term. Now I can get rid of this negative 19. Row 1 is row 3 plus 19 row 1 plus 19 row 3, and then I'm going to switch row 2 and row 3, and I'll be in reduced row echelon form. Now I can interpret this reduced row echelon form. This is my reduced row echelon form. It tells me that x minus 1/6 z equals 0, and y minus 1/6 z equals 0, and z is free. So let's give it a parameter, call it t, and I can now solve for y. Y is equal to 1/6 t, and so is x. And so my solution vectors, x, y, z, all have the form some sixth of a t, a sixth of a t, and a t. If I factor that out, they're all multiples of 1/6, 1/6, 1. And in particular, these are all multiples. If I think of multiplying everything by 6, these are all multiples of 1, 1, 6. So this gives me a simple vector that I can think of as my eigenvector. 1, 1, 6 is an eigenvector with corresponding eigenvalue of lambda equals to 21. And that gives me my third collection of eigenvectors, any scalar multiple of that. So we get to summarize. What we've done already, we found our eigenvalues by solving the determinant of a minus lambda I equals 0. Then for each of the 3 eigenvalues, we found the null space of the matrix A minus lambda I, and we got our 3 eigenvectors. Now to show how to check our work, what we're going to do is we're going to multiply each of these vectors by our matrix A, and we should find that the result is this eigenvalue multiple of our original vector. So here's our setup for our first example. We take our matrix A, we take our eigenvector, and we do our matrix multiplication. So our first row, 2, 1, 3, times our column, negative 1, 1, I get negative 2 plus 1, gives me negative 1. I now go along the second row, 1, 2, 3, times our column, we get negative 1 plus 2, that gives me 1. And then I go along my third row, 3, 3, 20, times my column, I get negative 3 plus 3, that gives me 0. And so what I find is A times this vector equals our original vector, and that's exactly what it means to say we have an eigenvalue of lambda equals 1. Now I've set up the second example. If I take my matrix times my vector, negative 3, 1, I should get a multiple of that same vector. So we start with our first row, and I'll get negative 6 minus 3, so we're at negative 9. Negative 9 plus 3 gives me negative 6. We go along the second row, 1, 2, 3. So negative 3 minus 6, that gives me negative 9 plus 3. So again, negative 6. And now I do the third row, 3, 3, 20. Negative 9. Negative 9, so that's negative 18. Negative 18 plus 20 gives me positive 2. And so what we see is the effect of that matrix multiplication. A times our second vector was actually double our second vector. And that's exactly what it means to say we have an eigenvector with eigenvalue lambda equals 2. Finally, here's the setup for our third. We'll take each of our rows times our vector, and when we take our first row, we get 2 plus 1 is 3, and 18, 3 and 18 is 21. We'll get that again on the second. And now 3, 3, 20, I get 3 plus 3, that's 6, plus 120 gives me 126. And this is 21 times our original vector. A x3 is 21x3. And again, we found an eigenvector corresponding to an eigenvalue of lambda equals 21. If you're given an eigenvector and you just need to check it, just multiply it by the matrix and see if it's expanded by a multiple. So we're done. We found and verified our eigenvalues and eigenvectors.